Welcome back, everyone. It is another wonderful Friday of the GMDSI hybrid learning class. I think this week we're finally going to get to some really exciting bits where we start to actually look at the inference that we're achieving by matching data from the past and all those sorts of fun things and the somewhat curious features that come out of that process. So we were going to start by going through the first part of the IES Basics notebook, and then we were going to take a detour and talk about response surfaces and use the response surface to try to visualize both how the Gauss-Levenberg-Marquardt algorithm functions in a deterministic setting and also how weights and noise affect your results, and just visualize that with the response surface. And then we would come back and Rui's going to take us home looking at forecast prior and posterior uncertainty kinds of things. So we're going to start with Briok going through the notebook today.
Great stuff. And I'm going to try and be as succinct as possible. So I was just having a flick through it before, and I don't want to go through like line by line, but I think it would be quite good to just look at like the overarching things of what we did in that IES 1 notebook. So that first one in the IES group. We're probably not going to get too deep down in the localization unless there are questions. And the restarting really is for people to look up on their own, because there's always a question: is how do we restart when we've stopped the history matching at one point and we want to pick it up again. So I'll just fly through this really quickly, especially this top bit. The main important points is we are passing the prior parameter ensemble through the PES-PP options to our PES control file. So that tells IES what our parameter vectors are that we want to run. And then we're also doing the step where we're drawing that observation noise covariance matrix, well, building the covariance matrix and then drawing observation noise from, so that's built from the weights, the observation weights that are on the that PES object. And then we're passing that to the obs ensemble option in the PES-PP options. And then we have a quick run where we just run NOT max 0, so just run the parval 1. And then we set a few other options. So there's this IES bad phi sigma, and we'll see that in action as we go through the rec file. But essentially it's saying if our objective function just goes a bit crazy, then we're just going to nuke those realizations. So it's a little bit greedy, but you know, Jeremy is greedy, so we're following suit. And the number of optimization iterations that we want to run, so we're setting 3 here, and then we just dump out the control file. And we spoke a little bit around pragmatic use of number of workers for your machine. And then we fire up IES, as Rui went through the other week. And we get a whole load of output. And this probably took a little bit of time. As it goes through the iterations, the lambda upgrades, the next iteration, more lambda upgrades, the next iteration, more lambda upgrades. We end up down the bottom. So I will just flick over to the rec file. So we get a lot of output here to the screen to stand it out, and most of that is also captured in the rec file as we progress. So I've just skipped down in the rec file to the exciting bits, and this is where I spend a lot of time when IES is running. Just keep an eye on how things are going, reevaluating where we are in the process and what things have been occurring through that process. So the very first thing we see is that initial phi. Remember, we got two measurements there. So we got the measured phi, which is including that measurement noise. So for those paired realizations, parameter realizations, and that draw from the observation ensemble, and then the actual, which is against the the obsval1, or whatever it is, obsval. And then we've got a little bit of information around what the maximum phi value was across all our realizations, and what the minimum and what the standard deviation is. And then similarly, we get this breakdown per observation group, which can be really handy to start seeing whether we've, right at the start in that prior run, whether we've got a reasonable balance in that objective function. And then this is where this bad phi sigma comes in. So we run the model n reals number of times. In this example, I think we're just running 30. So we have a bad phi threshold of 208,000. And so any realizations that yield a phi above that value are cut. And in this instance, we've got 1. So we're losing one realization. So now we're probably down to 29, if my maths is correct. And then we get another report of phi, and you can see the initial phi has now dropped significantly because we've checked out that realization that we decided wasn't performing well enough. So it's kind of a little bit of filtering in the process, automatic filtering in the process. I don't actually employ this a huge amount, but it's one of those mechanisms that you can deploy if you have some realizations that are just potentially doing some strange physical or unphysical things. It's quite a handy one for trimming those out. Probably don't want to do it if you're only starting with 30 realizations, but it can be a pretty useful one for helping constrain things. And then we get a repeated summary after that one's been dropped. And then we move on to the lambda testing, and I'm not going to dwell on this too much because I think Jeremy will probably touch on it when we look at the response surfaces. But essentially, one of the really cool things that we can do with IES is that we can actually explore, especially when you're in this parallelized space, so using that Panther run manager, you can explore multiple upgrade vectors or upgrade matrices at the same time, and find the optimum value for lambda and the optimum step length to help reduce phi quicker. And so we test a whole load of options for lambda and scale factor. And this is just then the result. So then we're running a subset of all of our realizations. So in this case, we're running subset of 4. And we're basically getting it from that. We're getting an idea of the best direction to go in our upgrade. So these are then the results of all of those. And then down at the bottom of this section, somewhere, stop me if you see it, we get to here. So then this is the best lambda and scale factor that is determined through that testing process. And then all that's left to do to complete iteration 1 is to run the remaining realization. So we've already run 4 of them. So we just have n reals minus 4 left to run to complete that iteration. And again, we check against that bad phi acceptance value. And in this case, we're now dropping another 2 realizations. So a number of realizations are dropping, but we are getting a better fit to our data. And that is pretty much the end of iteration 1. And then we do that 2 more times. And then eventually we skip down to, one of the other things that we get from that at the end of that iteration, at the end of each iteration, is an indication of how much each parameter group has changed. So this is the cumulative change across, or the aggregated change across all of the parameters that are in that group. So we can start seeing if some parameters are really getting wrenched in order to fit that data. So it's worth keeping an eye on these. And these are also outputted to CSV files as well by default, the parameter change summaries. So they can be pretty handy to keep an eye on. And then this is the mean phi sequence. So the prior, and then after iteration 1. And then we start solving iteration 2. And now I'm just going to skip down because the process is all the same. And then eventually after the 3rd iteration, we get, and remember n-op max is 3, so this will be the final one. We get our parameter change summaries, and eventually right down the bottom, we get that phi sequence. So we can see that we've gone from 18,000 to a phi of 128. So we're pretty happy at this stage, I reckon. And I will pass to Jeremy to explain what has happened, what magic has happened in that process.
Sweet.
There are a couple of questions. I don't know if you guys want to answer them first or.
Oh, yeah.
Yeah, we can take a shot.
So Chris Lee asks the $1,000,000 question of what number of realizations should we be using, and if there's any rule of thumbs for deciding.
Yeah, so I guess the rule of thumb is more. Yeah, so
right?
basically as many as you can tolerate is probably the best answer there. So there's some theoretical constraints around how many you should use if you have a certain amount of data that are orthogonal to each other. And also if you're looking at certain statistical moments of the posterior you're interested in. But I think in general, it's just as many as you can tolerate. You can't use too many, but you can use too few. And here I think we're probably using too few just to make a point that, we can use too few and then show you how using too few leads to missing some critical forecast results, which Rui will cover in a minute.
And the second part of his question is, how do we assess whether an ensemble has collapsed and if there are any metrics that can be used?
Ryok, you want to take a shot at that one?
Metrics, I don't know. Definitive collapse. Sometimes you would see it in like fitting some observations really, really, really well, at the expense, really well, as in your ensemble comes down to just a couple of bins at the expense of other observations that you might care about. But in terms of a metric, I don't know if there's a way of diluting that into a statistic.
I mean, I guess if the simulated outputs for historic observations is narrower than the noise distribution, then you would say conceptually it's you've collapsed too much. But I don't know if we ever really get to that type of phenomena. I mean, I try to look at posterior histograms of parameters into forecasts and then think about what kind of information content do I think the observations have. And if I feel like those distributions are narrower than I expected them to be given the observations I have, then I try to use that. But it's always post hoc and it's always very subjective.
Generally, if it's beyond belief.
Yeah, that's right. If it's become implausible, right? Like, no, that can't be right.
Then Tariq and Joanna both ask some questions which touch on the same thing. So Tariq is asking, how can you control the number of lambda tests and why would you want to change it? And Joanna is asking, what's a rule of thumb for a good subset size?
Good questions. You can definitely control the lambdas. You can test one, you can test as many as you want. That's up to you. I mean, like Briat kind of alluded to, I think one of the reasons PEST has been wildly successful is because of the multiple lambda testing. We'll see that in a minute on these response surfaces. The standard Levenberg-Marquardt algorithm doesn't test the lambda. It calculates the lambda based on the initial phi, and it keeps updating just a single lambda every iteration. And that does not work as well in all cases because of the nonlinearity of these inverse problems. And so testing lots of lambdas helps. And we'll see that graphically here in a minute on the response surfaces. And on the subset size, like I've moved to this percentage subset thing myself, where I try to do about 10% of the realizations in the subset, just because somebody showed me some results once that if your subset's too small, you can pick a suboptimal lambda, and that can actually give you bunk results later on down the line. Like you basically collapse too quickly into a region of attraction. So I try to use like about 10% of the realizations myself, at least in practice, for the subset.
One of the things that I find myself doing is looking at when I'm running on the server or running on multiple nodes, is actually being quite pragmatic about the subset size, the scale factor, the number of scale factors, and the number of lambdas, and trying to make them some tolerable multiplier of the number of nodes that I have available, just so I'm essentially using all the resource most of the time if I can. So yeah, and then as many of those options as possible. So as many scale factors, as many lambdas, and as big a subset as really as possible. It's a bit like the number of realizations. Is the more you can tolerate, I think probably the better.
Agreed. All right.
Right on.
Should I have a go now? All right.
I'm excited for this.
All right. All right. So now we're going to talk about the mechanics and the mathematics of the Levenberg-Marquardt algorithm, but we're going to do it in pictures, which I really like. So we're working in this folder, part 106 GLM response surface. Now there's a new notebook in here that you guys wouldn't have yet, but it's on the repo because we've just made it in the last few weeks. But we'll start with the original GLM response surface notebook. I think that is this one. Yes. Okay. So what we've done is we've taken a really simple, scaled down Freiberg problem where we've said there's only two parameters. Hydraulic conductivity everywhere in every model cell is one parameter, and recharge in every model cell in all times as the other parameter. So it's grossly simplified, but when we do that, then we can map out the response surface of the objective function as we change hydraulic conductivity and recharge in concert with one another. So every one of these pixels you see on this plot is a model run. So if we start down here, we said HK was a little bit less than 2 and recharge was about 0.5. Run that through the model, calculate the objective function, save that objective function. And then we sort of step across. So we just run a sweep across all those different combinations of hydraulic conductivity and recharge. And when we do that, we can make what they call the response surface. And so this is the error surface or the objective function surface, you'll hear it called, where it shows you where the minimum of the objective function is. And so in this case, our objective function only had groundwater levels. And so what we see is the classic, what we call trough of despair, right? This is non-uniqueness in pictures. And what it's telling us is what we would all recognize. If you don't have a flux measurement and all you have is groundwater levels, you can change recharge and hydraulic conductivity in concert with one another and run mod flow and get the same simulated groundwater levels as they relate to our historic measurements of groundwater. So anywhere in here fits the historic groundwater level measurements equally well. That's bad. That's non-uniqueness. And then we show that, well, actually, if we add some SFR flux observations, we're going to bring those in with this magic weight of 0.003, which Mike Feenan figured out after lots of experimenting is a good value to use. And we go, and now, oh, look how nice that looks. The trough of despair is gone. Now we have a nice closed bowl of our objective function surface. And so what that says is, since recharge is sensitive, or since the SFR discharge measurements are sensitive to recharge, we've now broken that correlation. So now we no longer will accept recharge values above, say, 1.3. If they get this high, we don't fit those SFR flux observations. And so now we have a nice closed bowl. And so we want, if we start anywhere on this surface using the Levenberg-Marquardt algorithm, we will eventually end up at this minimum. So the name of the game now is how do we get there in the minimum number of model runs? And that's where lambda starts to come into play. So first, we will use no lambda. Now lambda, it's a scaling factor where we increase the diagonal dominance of the approximate Hessian matrix. There's a matrix called JTQJ that's at the core of Gauss-Newton and at the core of Levenberg-Marquardt. When you start adding values to that diagonal, you make it more diagonally dominant, which means we take it away from being a Newton method and we start to look at it more as a gradient descent method. So when we have a really big lambda, We invert that matrix. A big number inverted is a small number, so that actually makes us take a small step in the gradient direction. If we use 0 for lambda, we take the pure Gauss-Newton direction. And as you know from, I guess, like rudimentary numerical analysis, Newton's method has that second derivative information. So Gauss-Newton approximates that second derivative. It has a curvature term. And so with no lambda, if we start right here and we solve, if we calculate a Jacobian with perturbation, so 2 model runs, do the finite difference thing, this is the Gauss-Newton direction that we're supposed to move. So boom, we step to right here. Then we perturb HK and recharge again. We get a new Jacobian. We form a new problem. We don't use any lambda. We step to here, and then we step a few more steps, and we're kind of at the minimum. So that's with no lambda value. That's the pure Newton direction. And I want you to just remember, this is where it steps to, right about this place. Now, if we use a medium lambda, this is what happens. So remember, gradient descent would be following the contours of the error surface, so this direction. Pure Newton stepped over to here, so a medium lambda is somewhere in between, and it steps us to this point. Then we do our finite difference Jacobian again, and we step to this point, to this point. So we're taking more iterations, we're going more slowly when we use a moderate lambda. Now, when we use a really big lambda, we get this situation. So we're basically rolling the ball down the hill. We're ignoring all the curvature information, and we're just doing gradient steps. Gradient step, gradient step, gradient step, gradient step, blah, 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 blah. It takes a really long time to get there. But this form of descent is stable, and it has some nice properties that if our problem is not approximately quadratic, the pure Newton direction can miss big time. But if the problem is quadratic, the pure Newton direction takes us right to the minimum. And so what we see is this is the point of big lambda, moderate lambda was here, and no lambda was here. So that if you kind of visualize that, we call that the trust region. And so that's why, Tariq, you want to test multiple lambdas, because it sweeps across that trust region and it helps us deal with a wide range of problems, because this error surface is very problem specific. You never know what it's going to look like. And in many cases, you can't even map it because you don't have more than 2 parameters, or the model takes hours to run, or both. And so that's why you test multiple lambdas. Now, there's another thing you guys may have heard of, backtracking in the ModFlow solver world. All you're doing with backtracking, if I'll go back up to this one, let's say, is okay, this is the step we're supposed to take, the direction and the magnitude to here. But again, if the problem's really nonlinear, maybe you also want to test some points along that trajectory. That's called backtracking or scale factoring. So we're basically taking that full vector and we're taking little steps along that vector that are shorter, because maybe we don't want to step so far because we're moving so far that we might like miss our minimum. Like if our objective function surface was some sort of narrow curving canyon, we might just step over it. So with backtracking, all we're doing is testing points along that line. And so then if you visualize what we're doing, we have this trust region and we have the endpoints picked out, and then we're sampling points within that trust region. So it's almost like a net that we're going to cast over that potential direction that we want to move and try to find the optimal place to step to each iteration. And so just to show you what that looks like, this is what PEST does. So you can see the value of the multiple lambda testing. So the first iteration that PEST ran, it tested that lambda, it tested this one, it maybe tested a couple others, and it said, oh, this is the minimum, let's go there. So you can see right away the value of multiple lambdas as opposed to sort of specifying lambda. We would ended up over here or over here. Those were our 2 best ones, the no lambda and the moderate lambda. But by testing several lambdas, we take a more optimal step. So we converge to the minimum faster. Are there any questions about the lambda bit? Let me go back to my screen real quick. Actually, if I do that, you're going to look at yourself. Are there any questions?
There is one come in.
Okay.
How can you prevent getting stuck in a local minima of the objective function and find the global minima?
Well, you have to use a global method. So we're already kind of in trouble here, right? Because this method can only go downhill. Now, the ensemble methods can step over dead spots of sensitivity and maybe through small local minima. But if you truly want to seek the absolute global minimum, you have to use a global method. That's the idea, right? But I think in many cases, our problems are pretty well behaved. I mean, PEST has been working on a wide range of problems for years and finding minima that are meaningful in terms of the values that are yielded for the parameters and the fit to the data. So I think in many respects, our problems are probably better behaved than we realize in that respect. at least as respect to this sort of global local minima problem that we hear a lot about. Buryak and Rui, you guys have any comments on that?
Yeah.
Sweet. Okay. So that's our response surface. Now, this is the new notebook. I'm really proud of this notebook. I've worked on it a lot in the last few weeks. What this notebook's going to do is take that response surface, and then we're going to run IES on that same 2-parameter HK recharge problem to try to understand how weights and noise affect the process. So all the fluff at the top, there's our same objective function surface again. Now, the first thing we're going to do is we're going to take this objective function surface, and instead of using Mike's optimal 0.003 weight, we're going to reset the weights on the surface water fluxes to just be 1% of the observed value, something that would be common, right? This would be like an error-based weighting type of scheme. Let's see what that does just to the objective function surface first. Yowza, right? We went from this nice closed bowl to what I would consider to be a much more nonlinear problem. Because now if we're stepping down this way to here, then we have to make a right turn to head for the minimum of the objective function. So just by playing with the weights and putting more focus on fitting the surface water flux observations, we basically turned this into a recharge estimation problem with a little bit of sensitivity on HK. So we're basically saying, if we can get recharge in that band of about 1.1, we're going to fit the data pretty well, but then there's more to be had if we can then stay in that band and move this way to where we get an HK of about 4. So, and this is something, again, I'm just starting to grapple with myself, is that the weights not only control how we fit the data, but they control the shape of the error surface, which means the weights influence how easy or hard the inverse problem is to solve. And then let's see that in practice. So we can run IS on the original problem, and we get this kind of thing. So each of these gray dots that are way out here, that's the prior ensemble, and then we use the scheme Briak was talking about. We run the prior Monte Carlo. We take those Monte Carlo results. We use that to formulate an approximate Jacobian. We make our JTQJ matrix. We test our lambdas. We upgrade. And then we finish off, or we do the subset testing. We pick the optimal one. We finish off that ensemble. And then we do it again and again. And we end up with these blue dots. Sweet. So you can see all the blue dots are sitting right about where we want them to sit, right around a minimum of the objective function. And we can look at what they would call the marginal plots, this blue distribution. That's our hydraulic conductivity posterior, if you will. And so you can see we've gone from saying conductivity could have this wide range to really conductivity is just from, say, what is that, 3 to a little bit more than 4. Same with recharge. Recharge, now we're pretty sure it's in the range of 1 to 1.2. Sweet. Well, let's now run that same thing on our goofy error surface. Look how much more difficult the inverse problem has become for IS to solve. So all the realizations move into this trough, but then once they're in this trough, it's a somewhat confusing gradient situation as far as IS is concerned, right? It doesn't know, I mean, they're getting there, but they don't have that sort of characteristic shape where they're following that minimum around, what is that, 4260. And that's because just by playing with the weights, we've made the inverse problem more nonlinear. Scary stuff. Now, you can use the multimodal solver. In this case, I was just playing with this, and you guys can go read about the multimodal solver. It does do a much better job of finding the minimum. So it's a problem with the global gradient approximation that IES is using in this case to actually try to find the minimum of the objective function. And the multimodal solver gets past that. So cool. One point I wanted to make, though, is, okay, so we've gotten to the minimum. Now we're saying, in this case, our hydraulic conductivity can be from about 3 to 3.5. Like, we're really sure hydraulic conductivity is right there. And recharge is even better. Man, we are so super sure the recharge is about 1.1 and that's it. That's a little bit scary, right? Do we really believe that we know recharge and conductivity that well from having some groundwater level measurements and some surface water flow measurements? I don't. So what controls the spread in that blue distribution, in those blue points? Well, in an overdetermined problem, such as this one, where we have way more data than parameters, The real source of uncertainty in the posterior is going to be the way we specify measurement noise. So let's do that now. Let's play with some measurement noise. Previously, we've been using weights as the inverse of measurement noise. So the standard deviation of the heads to this point has been 1 meter. And the standard deviation of the surface water flow observations has been actually pretty high, like whatever 1 over 0.003 is. So now let's make them more noisy and see what that does. So this is quite a bit more noisy, right? We're saying plus or minus 5 meters and 33% respectively on our two types of observations. And when we do this, now we get a much different situation. All right, we've basically blown up the posterior, and I like to follow this guy right here. This realization goes to here, here, and then ends up at this spot. And that's because this realization was given some extreme observation plus noise values, because we said the observations were so noisy and we pair each one of those parameter realizations with a noise realization. This one just happened to get some really extreme noise values, which gives it an extreme objective function value. So it's minimum, even though the true minimum is over here, its minimum appears to be way out here for it. Same with these guys, but that's good because what it's done is given us a spread out posterior, maybe something we're more comfortable with, maybe not, maybe this is too spread out. But you can see how noise, especially in overdetermined cases, is a dominant source of posterior variance. And then just for fun, let's pick some middle ground. Oh, I'm sorry, I did the multimodal thing first just to see if it was any different. It's not. And now we're going to take a little bit less noisy. So 3 and 25%, 3 meters and 25% for our noise measurements. And now we're a little bit, so we're not as collapsed, we're not as spread, we're in the middle. So again, you can see how the noise in these cases really controls the shape of the posterior distribution. And I think that was all I was going to say about that. Are there any more questions? You may have questions about Levenberg-Marquardt or noise or weights. I mean, these are big knobs to play with in your problems.
There's one question here from Wes on the upgrade direction. So are the upgrade directions for each realizations determined from a single empirical Jacobian?
In the standard solution, yes. But in the multimodal solution, no. So in the standard solution, we basically take the mean of the ensemble of parameters and the mean of simulated outputs, and we use that as sort of the center of the universe to calculate the gradient to use. And then each realization has its own residuals, so it potentially moves different directions, but that gradient, it comes from a global approximation or an ensemble-wide approximation. In the multimodal solution, we go realization by realization, and each one of those as the center of its own universe, and we approximate the gradient at that point. So each realization can move a different direction with that multimodal solver. And I might have a picture of that down here. Yeah, so this is going back to the trough of despair problem, just talking about non-uniqueness. You can see all the realizations that are on this lower quadrant are going the same direction because they all have the same gradient information. But when we go to the multimodal solver, things get a little more exciting. If I can get that stupid thing to open. There it is. Yeah, so now with the multimodal solver, you can see they're crossing each other and going their own direction for the gradient that was optimal for each one of the realizations. Again, this notebook has some words in it. Hopefully Rui can add some more words to it, but I encourage you guys to check it out. We'll share it with you guys. It's on the develop branch of the notebooks currently, but it'll be out there soon.
Question from Cecile. It's a good question. Why is it useful to look at both the measured and actual objective function summaries?
Yep, okay. So originally it was just measured, but I got myself in trouble quickly when I thought, oh, look, I have a really good fit. And then I started calculating the actual observations, though the noiseless ones, and it was a much different result. So I put both of them in there, and it's good to look at the difference between those two. If they're wildly different, then that might tell you have some sort of misspecification with the way you've set up your noise, because you would expect them to be at least within a couple of orders of magnitude of each other. But if one is like e to the 20 and the other one is less than 1, I think it's a good check for misspecification of noise. And the algorithm is using the measured unless you tell it otherwise. So it's deciding on the optimal fee and how to move based on measured, because this is because of, let me go back up, because of that behavior we want in the posterior, that we want this behavior in the posterior. But in a lot of cases, we're going to be concerned with actual results, because not everybody cares that we had noise realizations, that each one of them was fit well. They want to see how well does it reproduce the actual the noiseless actual observation. So we report both, just so you can get a sense that they're both going down monotonically, or is something weird happening and they're not. Yeah, that's a good question.
And a comment from Chris, he's happy with the notebook and visualizations that you just presented.
Yes. Success.
I guess people fire away any more questions that you might have on those topics. And whilst we're doing that, shall I share again, Rui?
Please, yeah.
And you can talk us through. We've been having fun with forecasts and forecast definitions, and in different people's versions of the notebooks. So, and Rui can explain what mine's doing and his isn't doing as we go through. So just you direct me, Rui.
Okay, maybe just scroll down to the forecast section, and we can go from there.
Oh, these are our lovely outputs.
There we go.
All right, yeah.
So flipping back to our Freiburg problem with the 30 minus 1, so 29 realizations at this point, I think. And so we got those amazing fits which Briok showed us. And now we, as usual, flip back to looking at the forecast and to see if we're actually doing a good job, because this is all synthetic. We know the truth. Of course, in the real world, we can't do these checks, but we're using this as a demo to explain things to avoid and how to cope with underlying issues in how to set up your history matching. So if you just plop down, please, to the thing. Okay, so here we have histograms of our prior, our posterior, and the true value of our forecast.
Might just have to zoom out a little bit for you.
No worries. So as we should all be familiar with now, gray is the prior, blue the posterior, and red is the true value, which we know because we have the answers at the back of the book. And in most of them, we're doing a pretty good job. After history matching, those blue bars cover the red line, the true value. So we're capturing the truth, except for one little case in the middle there, in which the posterior is completely failing almost failing to capture the true value. Now, this indicates that history matching actually made our ability to capture that forecast worse. So you can see that the gray bars capture the truth, but after we did history matching, our prior no longer captures the truth. So somewhere in the middle there between our prior and our posterior, we are actually at the ideal, but we've overshot it during history matching. And this is bad because it means our modeling is going to be incorrect, and we're going to give our client or our decision maker a incorrect forecast. Okay, so what's happening here is that particular forecast is one which is particularly sensitive to parameters which are in the null space. These are parameters or combinations of parameters which are not informed by the measured data that we're using as observation targets. So these are the most likely to incur some kind of history matching bias. Where are we? Lost you under fitting. Go ahead.
Oh, I'm good, man. Just hanging out.
Okay. Sorry. So the key point here is that even though we got a really good fit, perhaps we overfit our model, and this ended up in a bad forecast. So should we accept a worse fit, underfit our targets, our observations, to ensure that at least we're capturing our forecast in our posterior. So that's something that we do in the next few lines. We actually go back, and instead of using the third iteration of results, we use the results from iteration 1. And if you could just scroll down, and we see we get a worse fit with the data. Not so clean of lines, of blue lines over the red lines here, blah, blah, blah. But as we go down and we look at our forecast histograms, and now comparing the histograms on the left, which are for iteration 1, versus histograms on the right, which are iteration 3, we see that our posterior is now wider. So we're accepting a larger uncertainty or variance in our forecast, but at least we are not failing to capture it. So that is a strategy to take, but of course you can't know a priori if you've actually overfit or not. So how do you deal with that? Keep on going, please, Briok. So the easiest strategy, and we've touched on this already, is use as many realizations as you can or can afford or can tolerate. So essentially, the more the merrier. The more you have, you're less likely to incur spurious correlation. You're less likely to undersample your parameter space, and you're less likely to incur history matching bias. Carry on. And so what do we do here? Okay, so more realizations. So it goes through that, blah, blah, blah. And now we can compare the two. Again, we're comparing the two outcomes. On the left, 3 iterations, but with more realizations. So we've ensured we're getting a better fit with our data. But you can also see that we're no longer failing to capture those truths of the forecasts in comparison to the 30 realization 1 iteration case on the right. And they're actually pretty similar, but simply by having a larger sample size, we're more confident that we're getting a representative sample of the true population of parameter space. And so we're probably going to be more confident in our results. Yeah. Other coping strategies, there's a whole notebook on, so yeah, general answer is use as many realizations as you can. There are a few other strategies to deal with this stuff. So there's a whole notebook on localization, which we won't go into unless there are specific questions. But there's essentially methods to avoid incurring spurious correlation between parameters because of using a what's it called? The not perfect Jacobian. Forgotten the term right now.
Dirty.
The dirty Jacobian in the AUS method.
Fake Jacobian.
I think that's it. Yeah.
Yeah. Nice.
Oh, the last option is, of course, pray to whatever gods you believe in, but that might not go down well with the reviewers. Okay. Cool. So questions?
Couple of questions here. Cecile, just to be clear, if the observation data contains weight and standard deviation column, IAS will use the standard deviation to generate observation plus noise ensemble. And the standard deviation, if the standard deviation column is absent, IAS will use the weights. That's right, I think, isn't it?
That's right.
Yeah.
Or you can supply your own obs plus noise, or you can supply an uncertainty file for the observation covariance matrix. Like, there's options to separate the two, but I tend to use that standard deviation column unless I'm using autocorrelated noise.
I tend to draw my own realizations and then modify them in a very dirty way. But sometimes with some types of observations, for example, like some concentrations, if you draw observations plus noise, you might end up with some negative observations, which is a little bit funny to try and fit.
You know, I'm glad you said that, because I've seen people also do it with drawdowns, right? If they're trying to match pump tests in late time pump tests, the drawdown gets close to zero. And if they have any noise, they can have positive drawdown, which is an irreducible residual. But IES will try like hell to force the model. And how does it do that? It keeps turning up K, right? So it keeps turning up K more and more and more to try to get that, to try to make something happen that can't happen. And so you can specify a lower bound and upper bound in the observation data section of the version 2 control file also, if you want to truncate those noise plus observation draws so that you can keep at least non-negative concentrations and non-positive drawdowns from happening.
Yeah, nice. One from Tariq. On localization, I'm using spatial and temporal correlation variograms. Should I factor this into my localization distance? I assume this is the case. Otherwise, I may be overruling my predefined correlation to begin with. Correct?
Correlation only affects drawing the prior, though, right?
Yeah, that's. I mean, so the spatial thing we're talking about is the relationship between parameters and observations, which is not really local or linear, right? It's this sort of, it flows along the gradient. And so this is where localization is kind of a hack to try to help with the situation. So I think it's more about, what radius of influence do you expect around an observation well for conductivity to or for model cells with conductivity and storage to influence that. Or, I mean, it might even be like a window going up gradient. I mean, there's all sorts of like stream tube kinds of things I've seen people do with localization also, but I think it's always going to be a hack. So one of the things we put on the notebook is that imperfect localization can cause additional misfit as well. Like, so if you're too restrictive with localization, you can actually prevent the model from fitting the data very well. So I tend to go, just use more realizations. I think that's what I've been telling people lately. That's a lot easier. I mean, you can use some localization for like porosity and heads or backwards in time for boundary condition things, but when you get to the spatial level of K and water levels at different places in the domain, I think it's easier just to use more realizations. At least that's the way I try to do it.
Yeah, likewise.
That localized solve gets pretty slow as
Very
well
quick.
when that matrix gets big. So if you think you're saving yourself time by having fewer realizations, you might not necessarily be saving yourself time because the localization solve is expensive.
That's right.
Wes, I've commented on your question. If you mean the response matrix notebook, I think it's on the develop branch, right?
Yeah.
Oh, he actually means the IES notebook. Come on, Wes, you've not done your homework.
On the internet.
It's in the part 2, 6 IES. Oscar says, besides more realizations and localizations, when do you use regularization to help the ensemble against collapsing? Yeah, that's regularization and prior information.
Yep, so you can't use the prior information equations with IES. There is a regularization factor, but it's after the solve, not in the solve like it is with pests. So it's actually pretty inefficient. I tend to just use, if I'm worried about regularizing, you can use a big initial lambda so that at least your first iteration is small, right? Because we take a small step with a big lambda. And then I'll just look at those iteration 1, 2, 3 results and just choose one of those. If I think the third iteration is too fit, then iteration 2, iteration 1, you can step back and check those out.
There is also the option of adding observations, right? That kind of give you a little bit of information, give pest IS a little bit of information for the objective function, and those inequality constraints. So if your group starts with less or greater, then they work as an inequality, and the objective function is only penalized when that inequality is violated. It turns your problem pretty quickly into a nonlinear problem, but just maybe means that you can't rely on just iteration number one, as I would like to. Another question. I've been using localization on a project where it takes hours for each iteration due to the big amount of observations, even multiple threads. Is there a way to speed things up, or should I just ignore localization for this case? Yeah, it's definitely something that can happen, and also you can chew up quite a lot of memory. If it's a relatively simple localization case, so you're able to break it down by groups, observation groups and parameter groups, you can provide IES localization matrix that is based on group names, and that's a lot easier to solve. So it just becomes kind of another block solve. So I think that's a lot quicker, right, Jeremy?
Yeah, that's right.
Certainly what I've found. So yeah, if you are able to break it down by groups, so for example, isolating porosity parameters from head observations, and or temporal observations, if they're in a separate group for each time, and the parameters are in a separate group for each time, then you can isolate parameters from the future affecting observations in the past or being influenced by observations in the past. So if you can do it group wise, that's normally the quickest fix.
Or you can use more realizations, right? I mean, like how many, there's like this in the subspace sense, there's something called the solution space dimensions. And so if you have lots and lots of unique data, then that means you probably need lots and lots of realizations to honor all that data and prevent space correlation. But if you have, most groundwater problems I've worked with have 100 dimensions, 100 solution space dimensions, 200 solution space dimensions max, which means in theory, 250 to 300 realizations would be enough to avoid space correlations, more or less. Briok has seen some scarier things with the projects he's worked on, but I think if you run with 200 to 300 realizations and you're happy with the way the posterior parameter distributions look and the posterior forecast histograms look plausible and meaningful, then I'm not sure I would even worry about spurious correlation and localization.
It's a bold claim.
It's a bold claim.
Is that a referenceable claim? Jeremy White,
like on the solution space business. That's theoretical, right? That if you occupy the solution space plus a little bit more extra, since each one of the realizations are not perfectly orthogonal to one another, you ought to be able to fit the data to the level that you can achieve.
That's it for the questions. There's been quite a few questions about kind of rules of thumb and defining the rules of engagement, and we've probably been unsatisfactorily vague in our responses.
Fast.
but I think that is probably a bit of a reality. So it's often it's always problem dependent, and it's often a bit of suck it and see in terms of finding the right option for you for that specific project, for that specific prediction. But the overwhelming thing is probably, if in doubt and if tolerable, more realizations. Was there anything else we wanted to cover, or any more questions?
Maybe the notebooks for next time. So now we've done data assimilation and posterior uncertainty analysis, and we're going to pivot to something completely different. So now we're going to start on this idea of management optimization. And so management optimization, I think, is the next big thing in applied groundwater modeling, because it takes what we've called scenario testing and flips it around and does something much more rigorous with it to help identify optimal outcomes from modeling analyses, even under uncertainty. So taking this posterior ensemble we've been talking about today and parlaying that forward into a more advanced form of scenario testing. And so there's a few notebooks on that. There's I think Bria's got them up there. Yeah, there's part 2. Yeah, part 208 opt and 2. Those run pretty quickly. And then there's a notebook. Can you go to the MLU ones? So there's part 208, and then there's part 209. Part 209 will probably melt your computer, or at least run up your electric bill at home. So make sure you start that one well in advance of next Friday, because it will take a while to run this one. So what we're doing here is multi-objective optimization under uncertainty, which I think is the bee's knees in terms of decision support, but it's very computationally demanding. So, and you'll see that how many model runs it takes whenever you run these notebooks. So for next week, we're going to begin our foray into management optimization. So part 208 opt and part 209 MLU are the notebooks for next week.
Cool.
Sound good, everyone?
Did not think we'd get that done in an hour.
No, that was awesome. We hit it just right. Sweet. So any questions or comments over the week, again, open those on GitHub if you have any, or we can you can email us directly if you'd rather do it that way. And otherwise, we will see you guys next Friday.
Great stuff.
See y'all.
Take care all.